Okay, so like I said, today's going to be applications. The problem is, like, this section right here, this is chapter 6, section 7. It's called Applied Problems. It has some really cool problems that I just couldn't assign to you guys. Because like I said, we skipped something. And we're going to touch on it next week. When we come back on Tuesday, we're going to go do the thing that we skipped. But I don't, and it's one of those things. The way the book does it, I'm not necessarily against it. They bring it in and just say, press this key on your calculator. And then they wait till much later to talk about what you're actually doing. I don't like that. However, it affords you the opportunity to do a bunch of problems that we're going to have to skip. Really cool problems. At least your math teacher thinks they're really cool, so there's that. But anyway, most of these are just straight up, you set up a triangle. Like there's nothing new about what we're doing. We'll go over one or two. Then we're going to go way off into La La Land. And I'm going to use this as an opportunity to just talk about something really cool. Before we do that, I'll tell you why we're talking about it and why it's going to go way over your head. But there's method to my madness. So, okay. So first thing you need to know, and this is going to be for the rest of the year. This book will say something triangle ABC. Or it might be written as a little triangle ABC. And what they're talking about is we're going to imagine a triangle. And the big capital A, capital B, capital C refers to the actual points, these vertices. Now, in this homework, I don't think that any of that necessarily comes up. But they might say, like, it might say on triangle ABC, C, and they'll have a big capital C, is at 100 miles west and 200 miles north of some point. And so then you'd need to know that what they're talking about is that point there, C. I don't think, though, in this homework set, or in any of these problems, that the big A, B, and C actually matter. But what does matter, what's going to matter for the rest of the year and everything we do, is this convention, okay? And this is what it is. Each of these angles will always be labeled in the following way. The A will correspond with the angle alpha. B will correspond with the angle beta. And C will correspond with the angle gamma. And so this is like we get the word alphabet from the Greek, alpha, beta, right? Or vita as it's pronounced in Greek, but alphabet, alpha, beta, right? So this is how the Greek alphabet goes. It goes alpha, beta, gamma, and so that's what we correspond with our A, B, and C. And the thing is, and really, like I said, the capital A, B, and C are not going to matter much. But when you see that, that's what they're talking about. What does matter a lot is that the opposite side from the angle alpha is A. The opposite side from beta, that side is called B. The opposite side from gamma is called C. And yes, those are lowercase to contrast with the actual points, capital A, capital B, capital C. So the length of that is A. So if I told you the length B, you would know immediately that the opposite angle would be beta. That's how it's always going to be in this class. And it's going to be really important when we move on past this, later on, we're going to do something called solve the triangle. In this, you will be solving some triangles, and that means that you want to find all of these. In fact, I'm going to go ahead and get rid of the big A, B, and C. Is that you will want to find, you'll be given one or two, or you have to be given two. You'll be given two of these, and then you'll want to find all of the others. Now, in this homework set, gamma is going to be a right angle. That's just how it's going to be in this set. Later on, we're going to generalize and be able to do stuff like this. Alpha, beta, gamma. And so since that's alpha, this will be A. Since that's beta, this will be B. Since that's gamma, this will be C. And given any three of these, Given any three of these, so like an angle, a side, an angle, and a side, we'll be able to find the others. Or given an angle, and a side, we'll be able to find all the others. That's something we're going to spend some considerable amount of time doing.
A squared plus b squared equals, that doesn't work for
that. Does not work for this guy. It works if and only if that guy is there. And so we're going to need new tools for that. But there is a corresponding formula that actually, it turns out that when gamma is a right angle, the formula becomes a squared plus b squared equals c squared. But when it's not, it's a different formula. It involves cosine. Okay, so now, having said that, that's how it's just going to assume. It's going to say a triangle, side A and side alpha, find the other ones. And it's going to assume that you know that this is the setup, that alpha corresponds to A, beta corresponds to B, gamma corresponds to C. Okay? So, for instance, in number 4, where do I want to do this? 4. You'll notice you have 1 and 3. It gives you alpha is equal to 60 degrees. It says that C is equal to 6. Find the remaining ones. Given that, and like I said, in this, gamma is equal to 90 degrees. Okay, so...
Well, I know beta.
Okay, so if you know... Oh yeah, okay, so let's do that. So I'm going to go ahead and do it in the same orientation. I'm going to make that one bigger because I like my alpha to be right here. Gamma, it told us is 90, so I'm not going to write it. And so you said... And so here's beta. Now you said... So wait a second. You know what beta... What is beta?
30.
Yeah, it has to be, right? Because the sum of the angles has to be 90 degrees, and so this must be 30. And now, C, which one of these sides is C? The hypotenuse is C. And so that's 6. C equals 6. Now, this might... I'm going to go ahead and say that let's do this, that when we're doing this, let's go ahead and label these guys too. It's not so much a big thing now, but when we go to do it in general, where that's not 90, it can help keep everything straight if you actually give them names. And of course, we're going to name it A because that's alpha. We're going to name that one B because that's beta, etc. Okay, so here's the thing. We could use a similar triangle, right? We could say, wait a second, I know the 30, 60, 90 triangle. If that's 30... If that's 60, and that's a right angle, then this is 1, 2, square root of 3. And so I could say, well, if I need to make that 6, I would just multiply each one of these guys by 3, right? And so I multiply each of the sides by 3, and let's see what that gives me. 2 times 3 is 6. 1 times 3 is 3. 3 times root 3 is 3 times root 3. Okay? And then we'd have 60 here, we'd have 30 here. And that's great for problems 1 and 3. Like you could do that, but in problem 9, that will not be an option because they won't give you a triangle that you know. So I'm going to suggest that you don't do it this way for this homework set. And so,
Sine of...
There we go. Yeah, tell me something. Sine of what is what?
60 degrees is A over C.
I love it. I love it, right? Exactly. Sine is 60 degrees. And that's how I'm going to deal with this stuff, right? I'm going to say, well, this is a given, right? We have an actual given measure here. And so I could just say, well, sine of that thing is, by definition, opposite over hypotenuse. And so I go A, the thing I'm looking for, over 6. But sine of 60 is what? Sorry, sine of 60 degrees is what?
1 over
over 2.
Wait. No, just...
No, root 3 over 2.
Oh, no. 1 over root 3.
1 over... No, 1 over 2.
Oh. Root 3 over 2.
Sine of 60, here's 60.
Opposite over...
Opposite.
Root 3 over 2.
Root 3 over 2. So I could say, aha, sine of 60 is root 3 over 2. A over 6. I only have one unknown left. And so I bring him back up here. Root 3 over 2 is A. So that divides out and gives me 3 root 3, which we already knew because we did it the easy way, right? And so I could say, okay, then A is 3 root
3. And if I would have left that up there, we'd see that, yeah, obviously, that's what that is, right? Okay, let's do it. Let's do another one. And there's a couple different ways we could do it, actually. So the only thing that's left to find is b, lowercase b. How do I want to do that? Using some trig functions.
Cosine. Oh, using.
Okay, so cosine of what equals what?
Cosine of 60.
Cosine of 60
B
is
over
equal
C.
to b over c. There's another way we could have done it. We could have used this guy, right? We could have said sine of 30 is equal to b over c. That would have worked too. What's cosine 60?
1.
Yeah, 2.
No, 2.
No.
Wait.
No.
Cosine's
no.
never bigger than 1.
Yeah.
1/2.
1/2, right? Because there's 60. Cosine is adjacent over hypotenuse, so 1/2. So this is 1/2, and I wrote c. C is actually 6, so that's b over 6. 6 comes upstairs, gives me that, so that b is just 3. Could have done it this way.
Couldn't we have just used.
Here's 30 degrees. Sine of 30 is, lo and behold, 1/2. B over C is 6. Multiply both sides, you get 6 over 2 is B. 6 over 2 is 3. B is 3. I've written 3 there. I have solved that
Couldn't we
triangle.
have just used Pythagorean theorem? Find b.
You could. Once you have two sides, you could use Pythagorean theorem. That would be perfectly good. You could do that. So that's another way of doing it. And you'll see when we go to do the general triangle with either where this guy is not a 90-degree angle, then you can't rely on the Pythagorean theorem anymore,
Yeah.
right? And so, but sometimes you will want to use the general form of it. I told you it involves cosine and stuff like that. But sometimes yes, sometimes not. I'm not particular to any one way of doing this. Although I would say that you get in the habit of using the trig functions, like try to use the trig functions first. Like the similar triangle method is great when it happens to be 30, 60, 90, or 45, 45, 90. But in general, that's not going to work for us. Just like it's not going to work for number 9. Because number 9 gives you like the angle. It's basically the same setup. It gives you an angle on a side and tells you that gamma is 90. But the angle is like 35.3 or something. And so, yes, you're going to have to use a calculator. Okay? Make sure you've set it to degrees. Or if you're using Wolfram Alpha or something like that, it would behoove you to write it in and then put deg. So like if you're trying to compute sine of 35.2 degrees, you write deg. And Wolfram Alpha will know what to do with that. DEG, by the way. That's what I mean by deg. Okay. Okay. So that's that. Okay, here's another one. It says, given triangle ABC. So I'm already thinking, okay, so that means there's an alpha on the opposite side is A. There's a beta, the opposite side is B. There's a gamma, the opposite side is C. Given ABC with gamma equals 90 degrees. Told you that's how this was going to be. Express the first part. No. Express the third part. This will make sense in a second. In terms of the first two. What? This is what they give you. They say 18 gives you beta C B. So it's saying express the third part. They express B. Give me a formula for B, but the formula can only include beta and C. So let's just start with this. Given ABC, or a triangle ABC with gamma equals 90. Okay, let's just draw a triangle ABC with gamma equals 90. Here's gamma. It's 90. We'll call this alpha. We'll call this beta. The opposite here is A, the opposite here is B, the opposite here is C. So that's what they're saying. Now, we need to, so now, in other words, can we find some kind of trig function that involves each one of these things?
Sine of beta equals B over C.
I think you're right. Let's look at that. Because they've given you know that you have an angle here. You're not going to be taking sine of a length, right? Like, obviously, if there's an angle here, it's going to be some trig function involving that angle, right? So, okay, so I'm thinking there's some trig function. I'm going to plug in a beta, and I want B and C to be involved. Well, there's one I could think of. We have opposite over hypotenuse, which would be B over C if I take sine of beta.
You can do cosecant.
You could do cosecant. Let's try that. Cosecant of beta is equal to what?
C over B.
C over B. Okay. And so we could do with either one of those. But now it's saying express the third part in terms of... So in other words, get that one by itself in terms of the other. So what do I need to do here?
Just multiply by C.
Bring the C upstairs. And we get C sine beta is equal to B. And that's what they're looking for right there. If you did it here, we'd need to bring the B upstairs. Bring the cosecant downstairs. And I guess we could be done. Or you could say, well, that's the same thing as C times sine beta. Right? Because 1 over cosine is the... 1 over cosecant is the same thing as sine. Right? Yeah, okay. Now, another thing we could... So let's modify this a little bit. And let's say that instead of that, we want... Yeah, let's do that. Alpha and A. In terms of alpha and A, give me a B. We want to express B in terms of alpha and A.
Well, tangent of alpha
There you go.
equals A over B.
All I'm doing, and that's exactly what I'm thinking, because all I'm doing here is I'm saying, okay, we have an angle, and those are the two sides. And I'm not even using my brain at this point. I'm just touching here and going, oh wait, that's tangent, right? Like, take that angle, that's opposite and adjacent, and so I'm going to say, well, tan alpha is going to be that one over that one. I need to get the B by itself. So again, I'm going to bring the B upstairs, bring the tan downstairs, and have I expressed B in terms of alpha and A? Yeah. If you want, you could be slick and be like, well, that's actually cotangent of alpha. And yeah, you're right. That's fine. That's perfectly good. But that's sufficient right there. You have expressed B in terms of just A and just alpha. Okay? Any questions on this kind of thing? So before we get to the fun stuff, there's another thing I wanted to talk about. That's right. So there's a couple of things that's going to show. There are a couple of things that are going to show up. One of them is it's called the angle of elevation and the angle of depression, and that is the following. In fact, there's a picture in your book that's much better than the one I'm going to draw right now. Okay? So, as you look, whatever the observer, it's usually from the eyes of the observer, right? And there is one problem in your homework set that says that, somebody's holding a string 4 feet above the ground. That's going to be important to note in there. But that would be this line right here. The string is being held 4 feet above the ground, and then there's something up here. Okay? And so if you're here, and you're looking at, say, the sun, or the moon, or whatever that is, or, the smiley face, then the angle made from where you're looking to here, this is called the angle of elevation. Okay, so they'll just say the angle of elevation is x. Blah, 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 find the height of the thing, right? Or they could say, perhaps you're standing up on a mountain and there's somebody down here and you want to look, and et cetera, right? Then this would be called the angle of depression.
Sad.
It's very sad, and as a matter of fact, we usually denote it with a frowny face. This one, elevate, you know, if you're elevated, feel good, and so there's usually, I want to see this in your homework. No, don't do that. Okay, so that's just something to know. That's going to show up, and it's going to show up from now on. Whenever we do applications, there's at least one thing they'll say, the angle of depression is this. This is what they're talking about from the point of view of the observer. So for instance, in the quiz, I could have said that when I was describing you being right here, right, I could have said, and then there was the building here, right? I could have just said the angle of elevation, but we hadn't talked about it yet. So whatever. I could have said that the angle of elevation was 5.13 degrees. And then that would have taken care of all of that. But so that's what they mean, right? The angle of elevation. One more thing, and that's bearings. Bearings. So, on a map, you have north, east, south, and west. And a bearing is given in the following way. So, I'm copying straight out of the book. Let's say that this angle from here to here is 25 degrees. Then this bearing, this direction, would be reported as north 25 degrees east. And so, this is the way it is. It gives you your first direction, some number of degrees, your second direction. So, in other words, you go to the first direction, whatever that is. You go however many degrees towards the second direction. So north 25 degrees west would be the same thing, but in this direction. This right here would be north 25 degrees west. And I think it's always north or south. Yeah, north or south usually always comes first. So you wouldn't call this, you would not call the, what, oh man, what's 90 minus 25?
65.
Is it 65? Yeah, it's not 75. Okay. 65. Okay. So it's not west 65 degrees north. Though that does comport with what we just said, that's not what they do. They don't do it that way. It's usually either north or south, and then some measure going the other way. So I'm going to give you one. Therefore, what would this one be? If that angle right there is 55 degrees.
South 55 east.
South 55 degrees east. Is that right? Yes, that's right. Okay, so that's going to show up in a couple, and it will show up for the rest of the quarter, or the rest of the year. We're going to be doing, that's how, it'll just be reported that way. It'll say a ship sailed at 20 miles an hour for 5 minutes bearing this. Another ship left 5 minutes later and sailed in this direction. After 5 hours, how far away are they from each other? Or something like that. Okay? And that's the kind of thing we're going to have to do. I'm pretty sure there's one in here that does that. Pretty sure. And so, yeah, there we go. And so this is not, this homework set, I've chosen ones that are not that bad. I really want to do more, but we haven't talked about the thing that we have to do yet, and so I think it is worth it to wait and talk about the thing in full before we simply punch a key on a calculator. I don't like that. So let me give you an idea of what some of these problems are like. I'm going to do one here. This is number 34. Designing a water slide. Shown in the figure is, and they have a little figure here, is a design for a water slide.
It's kind of like jumps.
And this is what they give you. This is the information they give you.
It's boring.
They say that this, yeah, I know, right? 25 degrees. They say that this angle right here is 35 degrees. The height from here to here is 15 feet. The height from here to here is another 15 feet. And then they say that the entire length of the thing from there to there is 100. And what they ask you is to find the total length of the slide to the nearest foot. Clearly, they're not talking about this length right here. Right? That's not what they mean. They mean the actual line length of this thing.
Chop it into a triangle.
There you go. And this is what you're going to be doing pretty much for the rest of this class. Anytime you're given something like this, if you could break your problem into triangles, your life will be much easier. And so let's chop this into triangles because life, okay, so we have this triangle. So that's one. Here's another triangle. Boom.
And we don't
On
need
a
the other
rectangle.
one. Wait, do we?
It's just straight. It says just a rectangle.
Yeah. And so here's this is kind of what I'm thinking right now, right? Is like, okay, I'm going to go ahead and label this 15 right here. I'm going to go ahead and label this guy 15 right here. And what my mind is telling me here is that I could find this length if I know these two lengths.
Yeah.
Because if that's, say, 20 and this is 10, then I just take 100 minus off 20 minus off 10 and I'll know what this is.
Yeah.
And so that will give me that length. And right away, I can already see, think back to the very first thing we did, right? Or like actually everything we've done today up until now. If you could find that length given these two bits, what would that be? Like what trig function relates the unknown thing? And actually, let's go ahead and let's give some names here. Let's call this first length, why don't we call it x? This second length here, why don't we call it y? So that's from there to there. And this third length, why don't we call it z? And then, so I know that my answer, the answer that I want, is going to be whatever x is plus whatever y is plus whatever z is. Can we get z?
Yeah. It's
What is it?
sine of 35
There you go.
degrees equals 15 over z.
Sine of 35 degrees is equal to what?
15 over z.
Okay, and so what's the thing I want to get by itself?
The z.
Let's
So,
get the z by itself. So I'm going to bring the z upstairs, and I'm going to take sine downstairs. Okay, I'm a third of the way there. All right, so that's the first part. And like you could plug, and actually you'll want to, because you'll want to check your answers as you do this. Like use a calculator, plug that in and everything, and then check in the back of the book. But if you want to answer like this, and especially on a quiz or something, this is what I'll be expecting. This is that right there. Okay. So let's find x. How do we get x?
same thing, sine of 25 degrees is 15 over x.
And so I'm going to do the switcheroo for sine 25 degrees. There we go, 25 degrees. All right. Now, here's the hard part, finding y. I already told you how we're going to do it. Right. So actually, and let's go
100
ahead.
minus 15.
I want to go ahead and do this right here. 15 over sine 25 degrees plus the thing we don't know plus 15 over sine of 35 degrees. Okay, so I'm going to get rid of this now because that's how we got it. We know how we got it. Okay, so what do I do?
You need to
100 minus 15 over sine of
Sine
35
plus.
degrees minus 15 over sine of 25. Yeah. 100 minus both of them, right?
No, because if that would be what you're assuming. Right, I put A for answer, and I'm looking at that continuing area. This is the length of the slide, L sub S. The length of the slide has nothing to do with 100 here.
Yeah,
now
we have
we need the bottom one.
We need the bottom lengths, right? And so let's call this L1, let's call this L2. And so L1 is equal to what?
It'd be cosine, right? No, yeah, no, tangent.
I think it would be better to use tan. Here's why, okay? In the real world, if you're trying to figure this out, you've gone ahead and you've plugged that into your calculator and you get something. There's like going to be infinitely many digits afterwards, okay? Like, did anybody bring a calculator? Anybody? No, it doesn't matter. You know what I'm going to do? I'm just going to do it. I might as well, okay? So, let's do it this way. Okay. Come on, you. There we go. So, am I in degrees or radians? I'm in radians. I'm on degrees. Okay, so let's just test that sine of 90. Uh-oh. There we go. Okay, we're in degrees. Sine, or 90. Sine. I'm sorry, guys. This is probably bugging me more than you. 90 sine is 1. Yes. Okay, that's a great way to check if you're in radians or degrees. Try it, right, and see. Does sine 90 give you 1? Okay. So I'm going to go sine of 25. So 25 sine gives me that.
do it. Yeah.
Okay, so here's the thing. You're going to have 15 over 0.4226186, etc., etc. And so I'm going to go ahead and do that. Okay, so 1 over that is 2.3, that blah, 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 times 15. And here's the thing. What you're going to get is 35.49302, and then you're going to stop writing. It keeps going and going and going. You're going to stop writing because, of course, you stopped writing. Now, here's the thing. If you then use this to compute this length, which you could say cosine 25 degrees is equal to L1 over x. And so you go 35.493, and then you get lazy and you don't even bother to write the O2. It's not going to be as accurate, is it? Like you're chopping off digits. What you want to try to do, and this is why I recommend that you do write it this way, because then, like, you haven't approximated yet, right? And then if your answer is written out like this, then you could choose later on to approximate it whenever you want. And when your boss says, "Oh no, I needed 10 digits in order to figure this out," you don't go, "Oh, great, back to square one." You just tell your boss, "This is the answer. How many digits do you want?" And you plug all this into your calculator, and then you chop it off. Right? Does that make sense?
Yeah.
Why you want to do that? You always want to err on the side of more accuracy. And since 15 is given, we want to use that one with L1. We're assuming this is an exact given amount. Okay. So let's use that to find L1. What relates L1 and 15? 10 of 25 is equal to 15 over L1. So that means L1 is equal to 15 over tan 25. 25. There we go. So there's L1. Let's do L2. Tan of what equals what?
Tan of 35 is 15 over.
15 over L2. And so then L2 is 15 over tan 35 degrees. Now we can say, okay, now we do the subtraction. We say 100 minus L1 minus L2. So there's L1, there's L2, and we say 100 minus L1 minus L2 is going to be my y value that I'm looking for. And so plug that in right here. 100 minus L1 is 15 over tan 25 degrees minus 15 over tan 35 degrees. There you go. There's your answer. And you take that and plug it into your calculator. Of course, I mean, like, you could do these individually and all of that. It's just like, this is your exact answer right here. As soon as you start plugging those into a calculator, it's no longer exact. And now you're like, well, have I chopped it off too soon? Did I keep enough digits? I don't know. It's better to be able to do this and then deal with it later once you let your calculator deal with all of it.
Are, like, is like sine of a number that, like, of like a rent, like sine of 35, is that irrational? Is it going for, but as a decimal, or does it ever stop?
I don't know. So there are ones that won't be, like sine of 90 is 1, right? Sine of 180 degrees is
It's like
0.
a square root of any.
Yeah, and so like irrational now, but then again, sine of 60 is root 3 over 2, which is irrational, right?
Oh.
And so my intuition is that you can't tell just by looking at these, but to get something that's not irrational, it's probably not going to be anything that in degrees. You'd probably have to have a multiple of pi in there to get something that's not rational. That is, if you're plugging in something that's a rational number, and but you see, it's 35 degrees. You're not really plugging that in. See, this is the hard thing about this, is that what your calculator is doing is it's converting degrees into radians, and it's doing this, and so it's not really computing that, right? That's how we convert radians into degrees. You divide by the degrees, or 180 into pi, right? And so no matter what, you're throwing in an irrational number.
Yeah.
So there's a hope that it will be rational, but I don't know if I could generate. But I could tell you, like almost every single thing, the odds are that if you plug a degree measure into a sine or cosine, it's going to be irrational. The odds are very high that it will be irrational.
Yeah.
But I can't say for certain. I would need to sit down with that for some time. That is. And if you take calculus with me, we could ponder that. we could ponder that. We do need some calculus to start talking about why that's the case. Okay. So I really like these. That's what these problems are. You're going to be chopping stuff up, making triangles, all the cool stuff we can't do yet. But don't worry, we'll come back. We'll come back and do more of these. Let me just make sure there's nothing I wanted to say before we go way off into la la land. So yeah, bearings. One of them says it just gives you something that looks like this. It'll say north, east, south, west. And it's going to give you a bunch of these points. Point A, point B, point C, and then there's going to have different angle measures and stuff like that, and it'll say find the bearing. It's looking for what we just talked about, right?
Oh.
So for instance, if this is 35 degrees, you would say that the bearing at point A is what?
North 35.
North 35 degrees
East.
east. Okay. Okay, there's that, and then there is 65. Yeah, good luck with that. That's just gonna hurt. That's gonna hurt a lot. But you know, that's what the pain's good. Pain's good. Like if you've ever been to a gym, you know pain's good. Okay, now way off into La La Land. Here we go. So, part of the reason why I want to talk about what we're about to talk about is not just so I could put some really advanced looking stuff up on the board and talk about, stuff that interests me and whatnot. I had a few professors when I was at university who would every now and then just throw something out that just goes way over your head, but what it would do, it really sparked my interest in stuff. Like, there were plenty of times where I was like, well, I just got to know more about that. And like, it motivated me to keep going, right? And that's kind of what I'm doing today, but it ties into what we're, the very stuff that we're talking about. And really, in the end, it's not so much that, yes, I'm trying to plant some seeds here, but really, I want you to see something that, and I think this kind of blows my mind. It might blow your mind, maybe not, but let's have at it. So, there's something called the Schroedinger equation, named after, I think it's like Edwin Schroedinger, or Schrödinger. Yeah, you like that? You do German too? No, okay, it's just no, okay. So, but have you heard of quantum mechanics?
Yes, but
Quantum mechanics.
from Marvel movie.
Right, okay. So basically, in the quantum world, we're talking about the very, very, very small, right? Usually we're talking about atoms, electrons, or groups of atoms, but generally things very small. And I'm going to go ahead and do this. So this, by the way, what I'm writing out right now. So this is a function. Capital psi, or psi, if you like. Psi. Psi. It's a function of two variables. Position, which we're calling x, and t, time. Okay? And this function has this interesting property that if you take the magnitude of it squared, the absolute value, squared, what it gives you is what we call a distribution. You heard of a bell curve?
Yeah.
Okay? So like, if you imagine, whenever I think of a bell curve, like I think about taking everybody at, and this was, did all this stuff like at UW, and so I thought about at UW, let's take every student and line them up according to their height. And most people at UW will be 5'6". Is that right? One strike for 5,
Yeah.
2 for 6. Yeah. So if you line them all up in a row, most people would be 5'6". Okay? And then you have some people who are 5'7", and so on and so forth. You line them all up, and so we're imagining bird's eye view. We have everybody in a line, and we have everybody at the University of Washington line up. What would happen is that you would end up with this, we call this a distribution. And what you could think about then is this is like kind of the probability. If you think about kind of the area under this curve, and think about that area here, if we think about that as being one unit, then we could ask questions like this. What's the probability of being, say, either 5'5", 5'6", or 5'7", and going to UW? And what you do is, you'd count up this number of people, right here, and then you divide that by the total number of people that you have. Or mathematically, we could say, because now you could imagine, like now we're not at UW anymore, we're talking about like billions upon billions of atoms doing something or whatever. You could say, well, if we know the area right here, if we could find this area under the curve and divide it by or take the total area, divide it by that, then we could tell you what the probability is of being in that range, right? Everybody following me on this so far? Okay. So, the interpretation of quantum mechanics, I'm about to put some ugly looking equation on the board. It's actually quite beautiful. A very beautiful equation on the board. And the interpretation is this is a function that has the property that when you take the absolute value of it squared, you end up with a probability distribution. Probability of what? Well, of a, and that's actually, that's just, there's no, there's a lot of interpretations of this, but it's kind of like you can, it's kind of like where the particle is. So in this case, we're talking about x and time. So we think about, here's x, so this is your distance.
Oh, X is the.
X is an input and time is an input.
Oh,
Okay.
oh yeah.
X is an input and time is an input. And that makes sense because we're talking about physical systems.
Yeah.
Things change, don't they? Right? And so time probably needs to be, but it also depends on where you are and stuff like that. And so what this does is gives you the, and I'm glossing over some things, but you could say, where is this particle? Like if this is the front door, maybe, or this is the back door here, and, or let's just say, this right here is that corner, and we know we have some particle somewhere, and we want to know where is this particle? It's somewhere from here to somewhere over there. Where is it going to be? You compute this stuff, and it tells you the likelihood of your particle is that it's like right here. And the interesting thing is that it's never, it can't be in one place. It's weird because it's a distribution. You can never say, well, the particle is definitely right here. You could say, with whatever degree of certainty, with 99% confidence, I could tell you that the particle is from there to there. Because it looks like, because this is what the probability distribution looks like of where it's going to be. I'm glossing over some stuff, but this is just down and dirty kind of what this thing means. There's some function, psi, that has this weird property. Psi. And then you could also ask questions about momentum. How fast, given its mass, how fast is this particle going? And stuff like that. But that's what this is. And so this is called the Schroedinger equation. And it tells us about this function, psi, which is called the wave function. Capital psi, t. Now, I'm about to explain what all this stuff is.
Backward 6.
Yeah, backward 6. It's pronounced back 6.
Came up with these.
It said back 6. No. So, okay, a little bit of demystification here. This right here is a way of saying this is the speed with respect to time. So this is the velocity of the particle, or the velocity of its probability distribution. In other words, it's moving or something like that. This relates the speed of that particle right there. That's what that means. This d psi, dt, we're saying this is, and if you think about distance versus time, its change in distance is often denoted, and let's call this y. You would say the change in y over the change in t. You would say that would be its velocity. But then, if you're talking, as you make this smaller and smaller and smaller, we've kind of talked about this, and this is what you do in calculus. We say, what about as you make this really, really, really small and you make that really, really, really small, these deltas we write as d's. And so we're talking about, and so then this would be the instantaneous speed of a thing or a car or whatever. This is kind of the instantaneous speed of the particle. You can think about that. So it's the velocity of the particle, kind of. And then there's, yes, that's the imaginary unit. This is a constant. It's called Planck's constant. P-L-A-N-C-K.
Oh, I did not encounter.
Max Planck. And if you take chemistry, you're going to talk about this. There's a constant. And when it has a little bar over there, it's the same thing as Planck's constant divided by 2 pi.
Oh.
Oh.
Anyway, 2 pi, huh? 2 pi, interesting. Anyway, it's funny how that stuff kind of pops out. But anyway, and it describes, it turns out that, and so quantum mechanics, quanta. It comes from quanta, which means like a packet of something. It turns out that particles can't have just any old value of energy. That if you have, say, an electron, and I'm going to do the Bohr model of an atom, we have a nucleus right here. So a bunch of pluses and minuses, and pluses and minuses, and pluses and minuses. Neutrons
Neutrons and protons.
and protons.
But
Neutrons are neutral, right? Yeah. So no negatives. Thank you. How about zeros? There we go. Okay. So a bunch of these guys, and then you have an electron, which is negative. It turns out, so like it will be at you could think about it kind of as a distance, but it turns out it's kind of a probability of where it's going to be. Remember what I was talking about earlier. It's like, where is this particle in terms of x? And so if this is my x-axis, it doesn't make any sense to say that the particle is right here. It does make sense to say that there's a probability that it will be between here and here. And so, really, there's a probability that it's somewhere in this range away from the nucleus. But what the interesting thing happens is this. And you can kind of think about this as they're actually called orbitals, as though they orbit or something like that. But the more energy you give this atom, let's say you hit it with a photon of light, and what they found, and this is experimentally now, what physicists and chemists found, was that if you give it a certain amount of energy, it doesn't necessarily move by the same amount. In fact, you have to give it a certain packet of energy for it to jump up to what's called the next level. And it can never go between these two levels. And this is the weird thing. It's like as though energy is quantized. In other words, it's discrete. There are packets of energy. Like it's not like you could have, and the Planck's constant denotes, or it's related to the smallest possible unit of energy. You can't divide that by any more. So like if I were to give this 1 Planck unit of energy, it pops up by that much.
You can't give it half.
You can't give it half of one. And this is the weird thing about quantum mechanics. This is where the name quantum comes from. It's come from, they call these quanta of energy. There's a quantum of energy, or in plural, quanta of energy, that energy, apparently, by everything we've ever measured, it comes in packets. You can't have a half of a unit of energy. There's a smallest unit of energy. Ditto, smallest unit of, and then since energy and everything are related, also there's a smallest unit of time. There's a smallest unit of distance. There's a smallest unit of, and so on and so on and so forth. And so, really weird stuff. And people were like, how are we going to, because we had this model of an atom that there's these electrons that are just kind of zooming around, but it's not really satisfying. It doesn't really show what's going on in the real world, because the data we've collected say that it's not like this. It's sometimes it's here, sometimes it's here. It's never here. It pops up here. How do we deal with this? Well, some geniuses got together and came up with this. This is how it works. There you go home. No, and so, but what this is, and this is kind of interesting, is it relates, like I said, this is the speed of where that particle is supposed to be. This right here is kind of like the momentum. This is this is, you could think about this as being the momentum of the particle with respect to where it is, right? So this is the time, like how it's changing in time. This is how it changes with respect to where it is. So you could think about this kind of like the acceleration. And then there's this V. The V is the potential energy. Potential energy. So potential energy. If I take this right here, we are in a gravitational field. Gravity is operating on it right now. And if I drop it from here, it releases a certain amount of energy.
It's like kinetic.
It transforms from gravitational potential energy into kinetic energy. If I lift it up even higher, now it potentially has more energy. And when I let it go, it's even faster, right? We get even more kinetic energy transformed, right? So that's what this thing is. There's given any potential. And so this is where this comes down to. Is like, well, what are we talking about here? And the simplest, well, one of the simplest possible ways to think about, okay, we have a particle. What's it doing? Well, let's pretend that we put this particle in a box. And let's say our box is A units long. Okay. Now we could do this in 3 dimensions, right? Where we say, okay, so it's A units this way, A units this way, A units this way, and now we have a box and we're putting our particle in it, right? Everybody see that? We have some particle somewhere in the box and we want to know what's it doing, okay? But right now we're just going to look at 1 dimension of that box. So we're going to say, okay, you know what? I'm not too concerned about what it's doing in this direction. Not too concerned about what it's doing in this direction. I'm just going to look at 1 direction. And this generalizes. You could do all of this with 3 directions if you want. But right now let's keep it simple and just do 1 direction and say, okay, we're looking at 1 direction of the box. We're looking at the box face on. We know that there's a particle in the box. And in that box, as long as we're inside this box that has, length A, there's no potential energy. That is, we haven't pushed on it or anything. It's not being acted on by gravity in the way that this is. So we're kind of imagining a vacuum box in space, and we're going to take it and put a atom. It could be an atom. It could even be a small molecule. Actually, no, that's different. It has to be like an atom. It could be like a proton, if you want, just as long as there's no electric field on the outside, because if it's a proton, well, then now we're talking about there's potential energy, because these guys are going to pull towards each other, right? Because positive and negative, they attract, and etc. So we're imagining either it could be a proton, but then there's no absolutely 0 electric field around it, or whatever, right? Inside the box, there's absolutely no anything. And as far as we know, no initial velocity. We just have this is purely theoretical. We have some particle in a box, and we want to know what's it doing. Well, in the box, I told you, as long as we're in this box, the potential energy is 0. Okay, so that makes this thing much easier to deal with. So we're going to pretend now we're in the box. The potential energy is 0.
So all that stuff's
So all of this becomes 0, right here. And now we're dealing with this. This is actually doable. And what you do... Now, there are other ones that are doable, too. It just gets way uglier. So let's do this. But what you do... And this is... okay, I'm just going to burn through this. One of the first things you do is this. You say, okay, wait, this is a function of 2 variables. What if it's actually like this? What if it's actually 2 functions that's just been multiplied together? So for instance, right, like we say this is a function of 2 variables, and maybe it is actually, maybe we could write it like this, x squared plus 1 times, I don't know, how about 1 minus 2t? Like if you were to multiply this out, you'd get x squared minus 2tx squared minus 2t plus 1, right? And we'd say, there's my big function that describes all of the goings-on inside this box. The first trick is to say, what if we could rewrite it like this? What if we could take that thing, pull it apart, and we get this? You plug that into here. Magic happens. Magic just happens. And I remember when I was learning this, I gave my... He wasn't a professor, he was a grad student who was teaching the class. I gave him such a hard time about this. And I could tell he was like getting really annoyed with me. like where did that come from? You just say it's this and then this, and But then he explained to me afterwards, is like, this is, yes, you take this step on faith, but then later on we could justify that, yes, it does work out. Like this, like that when you do this and everything that we do subsequently to turn this really ugly equation into something nice that's actually solvable, turns out that there's really good reasons why you could do that, and you could justify it rigorously. For right now, when you first learn this, I say, just take it on faith. You can rewrite this thing. And when you do, so in other words, what I've done here is I've taken big capital psi, and I've rewritten it as lowercase psi times, so we're pretending there's two functions. Remember what I did? We had a big polynomial. I broke it up into just x's times just t's. That's what we're doing. When you do that, the t's kind of work themselves out in another equation, and you don't have to worry about it. And now all you have left over is this. I guess I'll rewrite it like this. Squared over 2m. M is the mass, by the way. I didn't say that. M is the mass of the particle. D squared psi dx squared plus v psi equals E. Ooh, what's that E? E turns out to be the energy. And if like you think about what I just said here, like what this thing works out to be, this is kind of like your momentum. This is your potential energy. And this is your velocity. Well, those things are all kind of related, right? Like you were talking about kinetic energy. Kinetic energy deals with velocity. That's also related, to potential energy. Potential energy, kinetic energy. This, when you get rid of the time, and so this is called the time-independent Schroedinger equation. Time-independent Schroedinger equation, where now you've assumed that this function is just a function of x. Becomes much, 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 much easier to solve. And you also get what your f of t is. Right now it's just magic. This f of t is just, it's kind of beautiful, but it's in the end, we're just going to take it and multiply it by the solution we get to this. This is what's called a differential equation. It's an equation where the unknown thing is a function. We're trying to find what function is this? Is it x squared? Is it 2x over sine? Is it, what is it? And so this tells us that the acceleration of it plus the potential energy times it is equal to the energy times it. And you could do some magic, and what pops out, this is where we've been going. So remember what this is. We're trying to find, we have a particle in a box. It cannot leave from here because there's a barrier. It cannot go past 0 in that direction, and it cannot go past A in this direction. Maybe they're like steel walls like 1,000 miles thick or whatever, right? It's not getting through there. But we know that there's some particle in there. There's no other potential energy. There's no velocity, there's no nothing. We want to know, where is it? What's it doing? This is what you find. Oh, first. How many solutions are there to that equation?
One. No, infinite.
0.
Wait, one. Okay, only x can. Oh, two.
There's two solutions, right? Because if you plug. Okay, hold up. Oh yeah. Okay. That one is hard on the eyes. How many solutions are there to that equation?
2.
There are 2. Both 2 work. Plug in a 2 and square it, you get a 4. Plug in a -2. You square it, you get a 4. How many solutions are there to that equation?
Infinite.
There are infinitely many. Sine x goes through 0 infinitely many times, right?
Yeah.
Right? I mean, and so what you could do is say then x has the form, in this case, you could say x would be pi times n, where n is any integer. Yeah?
Wouldn't it be pi over 2? Oh, no.
Not for sine. For sine, it goes here. There's pi over 2. There's pi. 3 pi over 2. 2 pi. 3 pi. 4 pi. 5 pi. And we get all the negative ones too, and blah, 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 blah. So we've seen an example of an equation that has multiple solutions. We've seen an example of an equation that has infinitely many solutions. And it turns out that this equation, the function, there are infinitely many functions that satisfy this. See, it used to be that there are infinitely many numbers that satisfy this equation. This, we're asking about a function. Turns out there are infinitely many functions that satisfy this, but they're very regular. And they look like this. So again, we want to know, what's the probability of this particle in a box? Where is it? Well, here's where it is. My whole point of doing this. Sine! Like, what? Right? This is crazy. So at the beginning of this class, I said this has nothing to do with triangles. Okay? Sine is this is sine. Okay? We started off by saying if you talk about triangles, it's useful to talk about these ratios and stuff like that. This is fundamental to the reality in which we live. Okay? Our physical reality, the best approximation, and this, by the way, this thing right here, it's scary. Like, I'm pretty skeptical when it comes to science and physics and stuff like that. Like, because I got a degree in math. I don't think highly of any of that stuff, right? Like, the thing is, with Newton's equation, force equals mass times acceleration, you could use that to land people on the moon. Okay? This is good enough to land people on the moon. Which means that you could get about 7 digits of accuracy. So if you're talking about where should I land in X, you could have 101 meters, 0.207, and da-da-da-da-da. And it's accurate about to 7 digits before it starts to break down. Because somebody called Einstein came along and said, that's not the whole picture. This thing, you're missing something here. There's a function in here that you're missing. But it's good enough to land on the moon, right? But nonetheless, this is still not quite accurate enough to be what we call reality. It's like, yeah, it's a nice approximation. This thing is scary how accurate it is. There's never been a time where it's ever looked like it's not going to work. It's like, we could use this to land people on the moon, and it's only good down to 7 digits. This thing's good as far as we've ever been able to estimate. It's scary how dead on this is. It looks like, now somebody might come along in the future the same way Einstein came along and said, this isn't exactly the whole picture. You're missing something. Somebody might come along in the future and say, this thing is not the big picture, you're missing something. But it's very unlikely. I mean, no. In the future, we have no idea about likelihood. I mean, that very well could happen. The way it looks now is that this is real. Like, in a sense that this is not real. You could land a person on the moon with this, but this is more real than that. It's scary how good that because this predicts phenomena in the real world, and it's so accurate that we've never been able to see how it could possibly be inaccurate. So then this is what should blow your mind. Look at that! The sine function describes where this bad boy is. Sine! This isn't a triangle, this is something deep. This is deep. What we're learning about is so deeply ingrained in our reality that it's like there's something there's something transcendent going on here. Like this describes, yeah, okay. So let's continue on, okay? We're not done because it turns out that with a differential equation, one of these things, yes, while this does solve it, if you were to take any one of these, take n equals 5, plug it in, it would work, and you're like, oh, okay, that's good. But with a differential equation, if any two of them work, then so does their sum. It also works. So it turns out that this thing, and remember what I said back at the beginning, is that's really not the thing that we're interested in. It's not this thing by itself. We're interested in the original thing. But we actually have a way of finding f of t. It's not hard to find. And in this case, in this special case, that's the thing. You can only do like 5 of these. And then you have to use supercomputers to actually like compute what's going on. But remember that the thing we actually care about, the function of both x and t, is this guy that we have times our f of t. And so it turns out that since there are infinitely many solutions, all of them work. So for instance, root 2 over a times sine 1 pi over ax plus root 2 over a sine 2 pi over ax plus, and so on and so on and so on and so on infinitely many times. And then there's some constants that get thrown in there and stuff like that. But here's the thing. This is what I'm getting at here. You put a particle in a box out in space, and you're just talking about where's this particle? Where is it? Well, it involves the sine function. Isn't that crazy? And when you add all these together and see what this thing looks like, and you go to compute the probability, and you look at this thing from 0 up to a, kind of looks like this. It's a bunch of dots.
So it's like,
where is it? Well, it's the probability is that it's kind of anywhere, but the interesting thing is like it's not here. It's not here. It's not here. It could be here. It could be here. And this and that and blah blah blah. And then when you throw, this is kind of this magic term. What this ends up doing is it just varies the phase. So it's like as time goes on, you could imagine these things just kind of moving this way. And so where is it? Well, and it's like, so and it turns out there's another thing in quantum mechanics that you could prove, and this is, it's so deep, it's in there, it just comes out of the math itself, that like if any of this is at all true, it makes no sense to talk about where a particle is. As you can kind of see, where is the particle? Oh, man. It could be kind of anywhere. It's weird, but I don't know. I wanted to bring this up because I mean, one, I would love it if you guys like got interested in this stuff and went on to like, well, I want to figure out what this is. How do you get from here to here? That's kind of crazy, right? On one hand, but also like just to show you that the stuff that we're talking about in this class, the sine function, it's not just to do these stupid applications. Like, you know, like how tall is the building? Well, or if you have a kite and you're looking at it and you know that you have this, how tall above this is it? Like, okay, that's great. That's nice. Or solve the triangle. Okay, yeah, we're going to solve a triangle. The stuff that we're talking about is somehow embedded in reality. Like that this... And it, you know, like I said, I hesitate to say, because of the whole Newton thing, it's like, is it really like reality? Because like Newton was off. Like, and yes, we could land a person on the moon with his equations, but it still wasn't the whole story. And since Einstein was able to come up with another part of it that we missed, like, did he finish the job? Or, you know, like maybe somebody else will come along and come along and do something like that. And it's like, something like that could very well happen with this equation. Like, somebody could come along and say, oh, you're missing something, or this is where this is wrong, you need to change this and that, and blah, blah, blah. And then we're kind of, you know, we'll always be progressing towards a better understanding. That very well may be the case, but I'm telling you, the accuracy of this thing is scary. Like, how accurate all of this is. There's not even a inkling in anybody's mind that this might not be that there might be some problems with it. In fact, given this and Einstein's equations, people are more likely to say it's probably Einstein that because you cannot really blend and do it very well. There's a problem trying to blend Einstein's theory, which is the theory of the very large, right? Like black holes and gravity and stuff like that. Trying to blend what happens with the very, very large with this, which governs the very, very, very small. And there's problems where they don't quite match up. Nobody out there is saying that there's a problem with this. Because that's how dang accurate it is. It's like, well, if there's any problem, it's probably Einstein that needs to change some stuff. This is so... And so, I'm not one to talk well about physicists or science for that matter, right? I'm very skeptical when it comes to stuff. This is eerie how well it describes our reality. It may not be the final say, but it's scary just how well this can predict experiments we do in the lab, things we observe and whatnot. And somehow, if you put a particle in a box and want to know where it is,
You still don't know.
well, yes, but sign pops out, which is just kind of amazing. So it's the stuff, so just once again, the stuff that we're studying and the applications of this stuff reach much deeper than just, there's this length and this height and this, that, and blah, blah, blah. This stuff pops out of fundamental things involving energy. Like ultimately, this is an equation saying the energy of this is the energy of this. And from that, we get sine. It's crazy. So I think that's all I got.